Good afternoon, ladies and gentlemen, and welcome to the webinar. My name is Auday Arawi from Intrinsic Limited. I just want to make sure that everybody is able to listen today and see the slides. Is it possible to confirm on the chat section? Just say yes or no, please. Yep. Hello again. If you've just joined us, welcome to the Introduction to TrueLoad webinar. If you can hear us, please just type yes on the chat section on the right-hand side of the webinar form. Okay. If you have a problem hearing us today, please just raise your hand or send us a message. Okay, looks like we're all okay. Right, good afternoon again. My name is Auday Arawi from Intrinsic. Today's webinar is about managing test data and FEA correlation using TrueLoad calculations. I will be joined by Dr. Tim Hunter, who is the president of WillStar Technology. Tim is the creator of the TrueLoad technologies, so he has quite a lot of skill in there, and today he will give us his experience in using TrueLoad. Intrinsic is the partner for WillStar Technology in the UK, and this would be one of many webinars to be hosted in the future. Can I just bring your attention as well to the questions at the end of the webinar? If you'd like to ask any questions, please type them under the questions tab, and we'll be able to answer them for you at the end of the session. Okay, I'd like to pass you now to Tim, who will give a bit of introduction about himself and so on. Okay, Tim, over to you.
Okay, great. Thank you, Auday. I'm very glad to be here to be part of this webinar today. We've got a in-depth presentation here on TrueLoad. Hopefully it'll give you a good introduction to the TrueLoad software and some customer examples. And I think we'll have something that will pique your interest and hopefully answer some of the problems that exist between FEA and testing. Okay. So just want to kind of kick it off with what I call the money slide. So this is we'll get into more detail on this in the end, but basically this is an actual customer example that when they looked at doing their test and development work without TrueLoad on the project that we worked on, they said that it would have normally taken them 30 weeks and $150,000 to do the project, and when we did it with TrueLoad, if you amortize the cost of the software, it was under $1,000 in 8 days. And we'll get into the details of that, but just want to whet your appetite with that, and we'll come back to that at the end, okay? So just leading with the money, just let you know what the potential is there with TrueLoad software. A little bit about me and WillStar Technology. So WillStar Technology was founded in 2010. Prior to that, I was with Harley-Davidson. I was at Harley-Davidson for 22 years. I was chief engineer of vehicle structures, and I basically was in charge of everything on the vehicle side of the motorcycle except for the electronics, wheels, and suspension. Okay, so I had the frames, gas tanks, fenders, styled surfaces, all the things that you see on the outside of the motorcycle. So any motorcycle that was on the road before 2009 has got my fingerprints all over it. So, and since we started the Wolfstar Technologies company and the TrueLoad software, we've got great development partners in Dassault Systems, ANSYS, MSC, CE-Tron. These are companies that have seen the value in our software and want to help us bring it to market in order to bring the value to their customers. So, the products from Wolfstar Technologies are these. Our flagship product is TrueLoad, and that's what we're going to spend the bulk of today on learning about. TrueLoad simply turns components into load transducers, and we do this by strategically finding strain gauge placement on the FEA model and extracting a correlation matrix between the strain gauge placement and unit load cases that the user puts in their FEA model. Then the users then go off and place strain gauges on the physical parts, measure the strains, and then we take those measured strains then and use a correlation matrix and back calculate the loads. So this is what TrueLoad is doing. It's basically making a load transducer out of your components. This is also partnered with a software called TrueQSE. TrueQSE stands for quasi-static events. And TrueQSE quite simply just takes results from your FEA model and allows you to linearly superimpose them via user-defined functions. And that's a straightforward approach. It's a very handy tool to do when you need to make some complex load cases. But what happens that when we run TrueLoad and we go through the test cycle, TrueLoad is going to generate time histories of loading functions that are going to be correlated back to individual unit load cases. So TrueQSE ends up being a post-processor for your loads that you measured with TrueLoad. So we bundled TrueQSE with TrueLoad so that if you buy TrueLoad and you generate the loading functions, you're going to have TrueQSE so you can query and quickly post-process and iterate on your designs. And then finally, the last product here is TrueLDE. TrueLDE is really aimed at a very narrow market for us. It's a post-processor for the Abacus linear dynamic results, and it supports star modal dynamics, star steady state, and star random response. It's basically a post-processing tool for looking at linear dynamic results in a very efficient manner. And then since the beginning of Wolfstar Technologies, we've had a close relationship with FESafe, and we've got direct interfaces to the FEA software, to the FESafe fatigue software, and other fatigue codes as well. We've got these nice interfaces to FESafe, so we can dump out basically macros and the data files that you need to run FESafe based on the loadings that you've measured. So if you've got FESafe, we're going to let you run FESafe much more efficiently, but you don't need to have FESafe in order to use TrueLoad, TrueQSE, and TrueLDE. Okay, so just to get right into Wolfstar Technologies' TrueLoad product, and we're going to get into the whole background on this. So basically, the motivation for TrueLoad is quite simply, what's the load? So if you were responsible for developing the components on this motorcycle, and as a design engineer or as an analyst, there's loading happening on here that's impossible to measure, impossible to calculate, but yet you as a design engineer, you as an analyst, have got to deliver parts that are durable and withstand the product's duty cycle. So what are you going to do? Well, what we do is they basically recognize that each of the components on the motorcycle are basically responding linearly. The swing arm, the frame, the crankcase, the handlebars, the fenders, the gas tank. These are all basically responding linearly. And so what we're going to do is we're going to place strain gauges on these components and back calculate the loads operating on these components from the environment. And like I said, we've got an easy interface to FESafe. Now this is a first-to-market solution. It's based on a technology called influence coefficients. Influence coefficients have been out there for about 50 years, but this is the first product that basically wraps the FEA model and the laborious task of choosing strain gauges and setting up correlation matrices with an automatic processes through scripting in FEA. So this is the first time that's really been done in a nice commercial beginning to end package. So TrueLoad will work on just about any products you can think of. So all of the products you see on the screen, we've got customers in these categories with the exception of the wind turbines and aerospace, but we've even got example applications in those as well. So if you've got products that are undergoing complex loading from the environment, from the users, from internal loading to the machinery, we can help you out to help you understand the loading on those components so you can design and develop those in an efficient manner. So when we think about product development and the product simulation workflow, this is a pretty standard methodology, right? You start with CAD, so you're using any number of the standard CAD packages out there. You have a nice 3D solid models. You bring those into your FEA preprocessor, and then you can solve those with, you know, Abacus, Nastran, ANSYS, whatever you want to use. And then, but in order to do those solves, you've got to come up with a load. So typically, you apply some loading on there that's coming from your company or that you've calculated yourself. And then once you've got these initial FEA results, you will often want to go into fatigue and use tools like FESafe or other fatigue codes out there to do the fatigue calculations. But in order to do those fatigue calculations, you've got to come up with a duty cycle and create these events. So these are things that you typically make up on your own. And then once you've done that, now you can go into the optimization loop and do design and optimization to improve your design. This is a pretty standard product simulation workflow out there. And when you look at this flow chart, you see that there are mature products on every one of the blocks in this flow chart, except for the loading definition and the event definition. There's no products out there in the commercial space that really give you that. And what I hope you'll see today is that TrueLoad is going to fill in those key pieces of the product simulation workflow. So if we just take a look at the traditional concerns with loading on doing an analysis, is that loading is typically the biggest unknown in analysis. So we can get a great solid model, we can put a great mesh on it, we've got great material models, we've got great solvers, but then you go in to put it in for a solution, and then you typically are guessing at what the load case is. And if you guess at the load case, you're basically guessing at the results. And we've got something in the U.S. that we call GIGO, garbage in, garbage out. So if you're not understanding the loading going in, you're going to get results that may or may not mean anything to you. And typically what people like to use are load transducers to try to understand the loading. But the problem of load transducers is that they can be as inexpensive as a load washer or as expensive as a wheel force transducer at $250,000. And the problem with taking a load transducer and bringing it into your system, you're changing your system. So you either got to cut out your system and insert your load transducer, or you add a wheel force transducer that adds mass. And so you're changing the mass, you're changing the stiffness, you're changing the load passing your structure. You're measuring something. They may or may not be the actual loads, but you're measuring something. And then the worst part is when you bring that back to the analysis community is typically working on the as-designed part and not on the as-tested part. So now they've got to rework your FEA model to look like the test part in order to use the load that you've measured in the field. So this is just not a great situation that analysts are typically left in. Another approach that people try to use is strain measurement. So typically what you'll do is you'll look at the FEA model and come up with some strain gauge placements based on some heuristics of your own. You might talk to some colleagues, come up with a couple of more strain gauge locations. Then you go to the field and you collect all the strain data and you look at these strain signals from the field and you look at your FEA model and you just scratch your head. You can't make heads or tails of the strain measurements versus your FEA models. The loading in the field is so complex versus the loading that you put on your FEA model. And typically what will happen is that you'll pick one or two channels of strain data at one or two locations and work for days, if not weeks, to come up with a load case that sort of kind of matches those strain patterns. And then you use those loads to redesign your part and do your rework on your part. And then the next time you get to the field to a prototype iteration, you'll find that you've missed something, and then you're back at it and doing it all over again. This is typical. I've done this in my past. I know you've done it. You do it too. This is a typical problem for FEA engineers. So what's wrong? Your companies are investing in high fidelity models. You got great analysts like yourselves. You've got world-class FEA software. You're doing the right things by testing with the right instrumentation, equipment, and data processing. And you're using, you're doing high fidelity fatigue with tools like FEA or other commercial FEA code, FEA-based fatigue codes. So your company is making all of the right investments, but they're not getting the right answers. What's going on? Well, the problem is you just got too many variables to manage. You got the gauge locations. You got the load cases. You got the quantity of data. So when you go out to the field and you collect these time histories of strain data, there could be 500,000 data points on that time history of strain data. And the problem is that every point in time, there's going to be a unique loading recipe for every point in time. And that's just something that you can't do manually. You can't come up with 500,000 different loading recipes to match the strain that you've got in the field. So you're just left spinning your wheels and you just can't get to where you need to go. So the solution here, quite simply, is TrueLoad. So TrueLoad does, in 3 words, what's called in situ load measurement. So in situ means in location load measurement. So we're going to turn your components into a load transducer, and we're going to do that by extracting a correlation matrix from the FEA model. And this works with all FEA codes. We've got very nice plugins for Abacus CAE and ANSYS Workbench, but we can work with any FEA code out there. We actually can even work with the Pro Engineer, Pro Simulate software, which uses the P-element approach. Okay, so we can work with any code out there these days, and what you get out of this is you get optimal placement of strain gauges, and you get nice direct interface to FEA, and we're making interfaces to other fatigue softwares as well. And you can go off and do fatigue calculations. You can use the loads that you measure to do normal part design and development to understand stiffness and deflection and response. So this is the tool for going in and understanding the loading in your products. So the workflow for TrueLoad goes like this. We start with an FEA model like normal, but rather than having you come in with one complex load on the FEA model, I'm going to ask you to decompose the loads into a series of unit load cases. So an X component of load, a Y component of load, a Z component of load, maybe a pressure load, maybe a thermal load, maybe an inertial load. But the thought process here is when you look at your part, you have to think if you could take all these unit load cases and scale them and combine them together, could you approximate the operating conditions on your part? So this is your thought process here. This is you being an engineer thinking about your part and thinking about how load enters into your part. You're just putting on unit loads. Now once you've done that and solved that for all the unit load cases, then the pretest software, the TrueLoad pretest software, looks at all the strain data on all the unit load cases and comes up with the optimal strain gauge placements. And then once we've got the optimal strain gauge placements, there's tools that allow you to reposition and reorient the gauges to make them convenient for the test engineers to lay the gauges. And then we extract a correlation matrix. So the whole point of pretest is that we're going to get the gauge placements, and we're going to extract the correlation matrix and store that to disk. Then you take those strain gauge placements from pretest, go into the lab, place strain gauges on physical parts, collect the time histories of strain data, and then once you've got those time histories of strain data, then we go back into the TrueLoad post-test software, and the post-test software then is going to take the measured strain data from tests and multiply it by the correlation matrix that we stored from pretest to generate the loading functions. And now we've got loading functions, and loads are loads are loads, and you can bring those loads time histories into your FEA model and apply them to your FEA model to reproduce the full field results on the part, to do design and iteration. And you can do that all manually with manual techniques in the FEA model, or what I highly recommend is you use the TrueQSE tool that comes with TrueLoad, which basically organizes all the unit loads and all the loading functions generated from the strain data and allows you to very quickly probe the model, generate X, Y plots for any node or element, generate full field operating deflection shapes, and allows you to go in and redesign and optimize your part on there. So I highly recommend you use TrueQSE. You don't have to. You can use your manual FEA techniques if you'd like. And then now that we've got loads, now we can go off with tools like FESafe then and do fatigue analysis as well. So now you can do design and optimization with fatigue software as well, and understand the durability of your parts now. So when you look at this whole flow chart here, the top 4 blocks are you turning your parts into load transducer, and the bottom flow chart are you doing design and optimization on your part now that you've got loads. So typically you'll do the top flow chart once, and then the bottom iteration cycle, you might go through that 20 or 30 times before you get to your next prototype level and you go back out to the field again. And then you might do the top 4 blocks again to refine your loadings as your part has changed. Okay? So I've got this player piano analogy that helps understand this technology a little bit. If for some people this works and for other people it doesn't, so please take it with a grain of salt. So if we were to design a player piano, we would study a normal piano and look at the 88 keys on the keyboard. And what we would do is we'd press each key and listen to the sound it makes, and we'd make a mapping between a key press and a sound. And I'm going to call that mapping between a key press and a sound, I'm going to call that a loading degree of freedom. I'm going to build a matrix of loading degrees of freedom for every key on the keyboard. Then we go off and we listen to an analog music, or we record the analog music with a precision recording device like our ear. And then we take that analog signal of sound, and then we project that analog signal of sound onto these loading degrees of freedom. And we're basically projecting this into the space of these loading degrees of freedom, or doing what a normal person would say, transcribing it into sheet music. And then once we've got the sheet music, then we can reproduce that into a player piano roll to reproduce the music. So this is what TrueLoad is essentially doing. So we'll take our component part, and we'll put a series of unit load cases on our component part. Then we'll create strain fields on the part. And then once you've got the strain fields on the part, then TrueLoad will look at those strain fields and identify strain gauge placements to identify each of the strain fields uniquely. So we'll get a strain gauge pattern that will uniquely identify each of these strain patterns. And then we'll store that correlation matrix to the disk. We'll place the strain gauges on the physical parts and measure the time histories of strains on the physical parts. And we'll take this measured time histories of strains, multiply it by the correlation matrix that we stored to disk to generate loading functions. And we'll get this nice time history of loads here that shows basically how much each one of these unit load cases respond in the full field of part. And then we can play that back together to reproduce the full field effects of what was going on in the actual part. So this has got a direct parallel to the concept of modal decomposition and modal participation functions. So this has got a very parallel mathematical approach to a concept that you may be familiar with modal superposition. This is using basically quasi-static loads to reproduce the full field events. Okay, so this is getting into understanding how this works with linear systems and loads. So a linear system is frankly where loads are proportional to displacements, displacements are proportional to strains, strains are proportional to loads. It's a linear system. Now I understand everything in life is nonlinear. We've got nonlinearities due to welds, we've got nonlinearities due to bolted joints, due to slop, due to contact, and I understand that that's what we've got, but we're turning our part into a load transducer, so we're going to stay away from these areas of a high strain gradients and only target areas in the middle of the part. The nominal areas of the part are where we're going to choose to lay strain gauges. So the loading can be as nonlinear as anything. The loading can be ramp loading, sinusoidal loading, impact loading. That's fine. I just need the strain response at the strain gauges to remain proportional and linear. So that's the only restriction here. Now we can take this diagram and turn it into a couple of equations. So the first equation here for the right-hand side, well, that's F equals Kx. That's Hooke's law. So if Hooke's law applies to your structure, then the left-hand side, which is strain times the correlation matrix is equal to load, is basically the strain corollary of Hooke's law. And we're going to calculate loads as being strains from tests times the correlation matrix from FEA. So earlier I said that this is based on the science of influence coefficients. This is the governing equation for influence coefficients. So if your parts obey Hooke's law, then we can apply true load to those components. Okay. So here's a little deeper look into how this all goes together here. So we've got strain times the correlation matrix is equal to loads. And so the way this all works here is that the loads on the left-hand side here, in this example, I've got 3 unit load cases on the FEA model, and I've got 4 strain gauges. So the strain gauges are the columns of the strain matrix here. So we're going to have four uniaxial strain gauges laid on our part and 3 load cases here. And I don't think I get into the detailed mathematics here, but I just wanted to give you an idea of what this is. And if we want to do a follow-up presentation, I'm more than happy to talk to you individually. We can go through the detailed mathematics on this. Okay. So this is actually my training example that I use in my trainings for true load. And in this example, the analyst here has got a headlamp from a motorcycle. So the analyst looks at this headlamp and says, it's getting excitation from the front suspension, from the handlebars, from the frame, from the engine vibrations. The analyst says, this is basically going to be a base excitation problem, and he's choosing to make the unit load cases here as being restrained to ground at the bolt locations, and you're going to put X, Y, and Z acceleration loads as his unit load cases. So this is a choice the analyst made here for solving the FEA model. So once he solves the FEA model, then he can just go into the true load pretest software, and pretest will then load up all of his 3 unit load cases here for his X, Y, and Z unit loads. And then he's got to select a subset of the model for placing strain gauges. So he clicks this little button here, and he'll select a subset of the model to get the strain gauge placements. So notice he's picking elements in the middle of the headlamp bucket and in the middle of the legs, and he's staying away from boundary conditions, and he's staying away from where parts hook up to other parts. He wants to have nice, nominal, linear locations for placing the strain gauges. Then it tells the true load software that he wants 6 strain gauges and pushes the find strain gauges button, and it draws up the strain gauges on the screen and shows them the position and orientation of each of the uniaxial strain gauges on the component. Now, once he's happy with those strain gauge placements, he saves the TLD file, which is going to store the correlation matrix to disk. He goes and then places the strain gauges on the physical parts and measures the strain on the physical parts in a physical test. And the whole idea now is to take this measured strain data then and turn them into loading functions. And we're going to do that with the post-test software. And post-test is going to take the TLD file from pretest, which has got the correlation matrix in it. It's going to bring in the strain data file from test. And then he's going to push this button here to generate the loads. And it's kind of that simple. Now, there's other things here for mapping and dropping channels, for plotting data, for setting things up for FE safe. But really, at the end of the day, it is you just bring in the C matrix from pretest, you bring in the strain data from test, and you push the button, and you get the loads. And then once you've generated loads, then you can always go directly into FE safe to do fatigue analysis if you'd like. But what I highly recommend you do is you go into the True QSE tool, the quasi-static event tool, and this gets generated automatically when you generate the loads. And you can see we've got our 3 unit load cases here, and the loading functions generated from the strain data. So these 3 loading functions were just generated from the strain data, and they correspond to each of one of our unit loads here. And we can probe any node or element for any data component of data we want, displacement, stress, strain, whatever. Or we can generate operating deflection shapes, or we can go off to FE safe to do fatigue analysis. So these are all things we can do, and so this is great. And the whole point now with true load is now that we've done this first for our initial part, now we want to go in and do redesign. And so the redesign methodology will work like this, is that, well, once we've done this once, we can go back to the original part, we can come in here and we can poke holes in the FEA model, we can thicken things up, we can remesh it, and the only requirement I'm going to place on you now is that you just solve it with the same 3 unit load cases you started with. So a very simple FEA solve now is the same 3-unit load cases we started with. I'm going to have you solve that new structure with that. And then all we do then is come back into QSE and point the QSE quasi-static event to the new FEA results file, and then it will linearly superimpose the results accordingly by the proper loading functions. And now you can see the response based on all of your unit loads that you've got in the part and the time histories of loading functions you've generated. And you could also go off and bring this off to FESafe and use the FESafe scale and combine methodology to do fatigue calculations as well. So that's basically the workflow for true load. Okay. So at this point, we're going to go into some customer applications. So this one here is an application that a customer had on what's obviously a bulldozer here. And when I came and talked to this customer, they had actually already launched this bulldozer, but they had a horrible time in development. In development, the FEA analysts could not match anything in the lab couldn't match anything in the field, and each department thought the other department didn't know what they were doing. So there's a little bit of an internal war going on. And when I sat down with the managers of the test department and the manager of the analysis department here, and I showed them what TrueLoad could do, they said, Tim, we don't care if this works. If you get my analysis guys to talk to the test guys, we'll consider that a win. So we did the project, and working with the engineers there, we put X, Y, and Z unit loads on the front of the blade here. There was a hydraulic cylinder here we had to actuate, so we had a load there. There was a mechanism on the back we actuated. So we had about 5 unit load cases on here. We put 12 or so strain gauges on the arms and on the back of the blade, and we measured the strains in the field. And what you're seeing on the top right here is the measured strain data in green. So the measured strain data is in green, and we take that measured strain data, times a correlation matrix to generate the loads. And then once we've got the loads then, we can go back into the FEA model and pull up the simulated strains in blue. So the green is measured strains, the blue are simulated strains, and when they saw this plot, they were really thrilled. They thought, this is great. What a great job you've done matching the strains. But they said, this is all nominal areas. And what they're really concerned with were the areas by these welds here on these forgings here. So these forgings here were their areas of major development concerns on this bulldozer. And so they had laid extra strain gauges, so like this gauge number 19 here was laid on the model on the physical bulldozer. And then we went into the QSE software and we probed the elements coming away from the weld there on the physical FEA model, and we plotted that up. So the green data here is the physical strains measured from gauge number 19, and the colored curves are coming from the FEA model and showing how well we were able to match these areas of high strain gradients with this. So this is a nice example that says when you get the overall flexibility right, then the areas of high stress concentrations come along for the ride. So, all right, here's another example. This is the crankshaft on a small engine, and this customer, after we talked to them, they had said that they had problems with their crankshafts in their dynamometers. So their crankshafts were breaking on the flywheel end of the crankshaft, and this is a problem they'd been working at for probably 2 years when we talked to them about it. And so they asked if we could help with it, and said, well, I don't know much about crankshafts, but let's give it a try. So working with the engineers there, we put X and Y unit loads on the crank pin here, and they said they knew that there was modal content from the flywheel, so we also included the flywheel in the model. I mean, we had the torsional mode and 2 bending modes of the flywheel. So we had 5 load cases. We laid strain gauges on the crankshaft here. And then what I'm showing you here are what I call my bob and my wow plots. So the best of the best, the worst of the worst. So the bottom plot here is showing the green is the measured strain and the blue is the simulated strain, and they are line on line, less than 0.01% error. And even my worst strain gauge here that I had on this part, I had about 1% strain error on this, and this was my worst strain gauge. And so when I reviewed the loading with the engineers at this company, and I showed them the loads I calculated for the crank pin loads, they said for the speeds the engine was running, they thought that seemed about right. So we took the loadings I measured, we ran that through FEA, and FEA then identified the area of maximum damage, which corresponded exactly with where they were failing in their dynamometers. So this is a really nice example. This company was working on this for two plus years, couldn't come up with the answer, and I was able to work with them, and in 6 days we came up with the loading conditions that caused this failure. And what I like to say about this is that these engineers had all the unit loads. They understood the loading coming in. So they had the ingredients, they just didn't have the recipe. What TrueLoad did, TrueLoad provided them the recipe and how to mix all these loads together to create the proper loading conditions to reproduce the failures on their part. Okay, there's another advanced application here that we've got in TrueLoad called sliding load applications. So this customer creates cranes, and so in all the examples I've shown you so far, the loads haven't been moving. But on these booms, on these cranes, the loads are actually sliding along the length of the boom as the crane is extending and retracting. So we had to have a way to come up and get these loadings. And so what we can do is we can identify the stationary loads where the loads are always present on the boom, and then we can go through and set up a series of unit loads at locations along the length of the boom, and we'll store up a correlation matrix at one location and go to the next location and store up a correlation matrix at another location. We store up a series of correlation matrices and the position of where those correlation matrices are, and then when we lay strain gauges on the part, we collect the strain data together with the position of the boom, and then we can turn the correlation matrices on and off and linearly interpolate between them as the boom is extending and retracting. And here are some results from the test we did. So the bottom left plot is my blue and green plot, where green is measured strain, blue is a simulated strain, and that looks like a mess. So I did a cross plot right next to it here. So on the horizontal axis is measured strain, vertical axis is simulated strain, and you can see that we've got pretty close to a 45-degree line. So that's 50-some strain gauges, 90-some odd unit loads, and we're getting excellent correlation. And so this gave this manufacturer all sorts of insight into what's going on in this. They were able to create design rules for generating the next generation of booms with this style of crane. All right, I've got two more examples here. This one is kind of my favorite one these days. This is a Baja Car Suspension. I hire college students from the local university here in Milwaukee, and it just so happens 2 years ago I hired the guy who was in charge of the FEA Baja Car project at the university here. And what they wanted to do is they wanted to use TrueLoad to improve their design. So I basically coached them on this project here, and they went ahead and did it. So they wanted to improve the suspension arm on their design. So we turned their suspension arm into a load transducer. So we put on XYZ unit loads on the shock support, XYZ loads the wheel, top and bottom stabilizer links. We also included some moments in here. So we had these unit load cases on this arm here, and then these are basically animations of all the unit load cases. PowerPoint doesn't like to animate that many different types of animation files. And then basically TrueLoad went in and told them to place strain gauges at all these locations here. So you see that most of the strain gauges are laid on the forging upright here, because that's where most of the unit loads are. So you got your load paths on that. But also we've got strain gauges on the load paths on the arm itself. So we got strain gauges located on the arm and on the upright, and we placed 16 strain gauges here because it only had 16 channels of data collection available to them. And so these kids who did this I mean, they had really never done an FEA model other than in class before. They had never touched a strain gauge. They had never done any data collection. They had never programmed any instrumentation. So they did this project from beginning to end inside of 6 weeks with my coaching, but they did all the work, and I bought the strain gauges, and they got really, really great results here. So here's an example. They actually built jumps in the parking garage, so we took data off jumps, 0 to max brakes. We did hard turns, and they took all this data, and then they got results like this. So again, here's the green curves here are the measured data that they collected from this, and what you're seeing here is actually the jump that we just saw the video of. So the green data is the measured strain data, and we took this measured strain data, multiplied by the correlation matrix to generate load histories of the loading here. So here's our 11 time histories of load on the part. And then once we had those time histories of load, then we can go back into the FEA model and reproduce the strains on the part. And so we've got the simulated strains in blue here. And then there's a cross plot here of the measured strain versus the simulated strain. And that looks like a really nice 45-degree line showing that we're getting great correlation. And then once we've got that, then we can create the full field operating deflection shapes. So this was great, but the students wanted to reduce the weight on their suspension arm, and so they went through a redesign cycle. It was a pretty simple redesign cycle. They had created a duty cycle event of so many hard brakes, hard turns, and jumps, and then all they did was they looked at their initial repeats where they had 278,000 repeats of this duty cycle, and they just went through an exercise of reducing the tube thicknesses, and they were able to bring that durability down to being 12,000 repeats, which is still more than they'll ever need on this proving ground bike, and they had a very nice design. So they saved 25% of the weight. You're just doing some different, very simple shell thickness changes to these tubes, and they wrote a paper on this, and it was presented last year at the, I've got the wrong date on here, is April 13th, 2016 on the SAE World Congress, and there's an SAE paper on this, and they did a great job with that. And this is my last customer example. So thank you for bearing with me here. So this is Aaron's. They make these high-end lawn and garden tractors, and they've got this engine deck which sits underneath the seat here, and there was an engine sitting on this thing, and this was working fine for them, but their transmission supplier needed them to provide more airflow here. So they got with me to see if I could help them out. And working with the engineers there, we decided to put X, Y, and Z unit loading on a lump mass attached to this plate here, because it's basically getting ground excitation from the environment. And just as an aside, we also did a modal version of this, which I'm not going to show. And then from these 3 unit load cases, we had 8 strain gauges placed on here from true load, and then here's their data. So what you're seeing here is my typical green plot of all 8 strain gauges on their proving ground, and then there's blue curves from the simulated strains, and you can see their line on line, and look at this excellent cross plot we got. So this was literally a single button push on my part to get to the point of getting this type of strain correlation. And the beauty about this project is that this customer had already started on this redesign methodology themselves, and using their traditional loading technologies and their loading design rules on the part. And they had their initial design that they ran through FEA first, and they had it on shaker test the day I was there talking to them about this, and they're bringing me to the lab to show them their first design iteration on this, and they brought me there, and the part had failed in the lab, and this part had failed in 12 hours in the lab. It's supposed to go 10,000 hours. So this part that you see here had failed in 12 hours, and I said, perfect. Give me the FEA model of that one. Let me take the loads that we just measured, run it through that, and then working with the engineers, we came up with a different hole pattern and different material thickness and riveting configurations. And by the end of the week, we went through 5 iterations, and we had come up with a design that works. And I'm going to show you some durability results here on this. So here's the durability results on their initial design. Here's the durability calculations. Their goal is to be at 10,000 cycles. So what we want to look at these durability plots, we want to see yellow, green, or blue. There's some red here because of our RBE for the lump mass in the engine. And then look at this. Here's what FE Safe is predicting for their initial design. So FE Safe is predicting 10 hours of repeat, and they in the lab we actually got 12. So this is nice confirmation showing that we got the loading right, and then again going through different design iterations. By the end of the week, we had the airflow they needed with better durability than they started off with. And just coming back to the money slide on this, this is just showing that when we talked to the engineers, they said that each physical iteration cost them about $30,000, 6 weeks to procure and make the parts. And we went through 5 iterations, so that would have been $150,000 in 30 weeks of time, and guessing between each iteration for the loads. And with True Load, we bought some strain gauges, we instrumented things up, and it took a couple days during timing, and it took us less than $1,000 of amortized cost and 8 days of time. So, and we actually got the solution that works, and we're able to do it right the first time. So this is what you can get when you can understand the loading. You can understand how to design your part right. So this is my summary slide here. The whole point of True Load is that we're going to give you optimal strain gauge placements. We're going to turn your parts into load transducers. You're going to get strain correlated load histories, and you're going to be able to reduce your test time, your test costs, because now you're just buying uniaxial strain gauges for your testing. So uniaxial strain gauges cost about $10 a piece to take about a half an hour or so to instrument. So you compare that to buying expensive load transducers or accelerometers, not being able to make heads or tails out of the data. So we can really reduce your test costs, and then you're basically going to get excellent test correlation, and now you can use those loads then to do the right thing by design, and the engineers and the analysts will go in and give you the right design and analysis tools, and you'll be able to make the right design decisions in FEA, and you'll end up eliminating whole iteration cycles because you've got the right design and analysis loading going in, and you're going to make the right design decisions, and you're going to make less hardware iterations, and that's going to be the huge savings that you'll get in all of this. So, and then a couple other things that we didn't touch on very much here. I introduced sliding loads, but we've got this technology called hybrid loading, and contact control is a brand new feature we just introduced this year. So these are great technologies that you've got available to you here, and we can handle almost any complex loading situations you've got. So with that, I think we're going to be ready to take some questions. I see we've got several questions coming in here. Let me see if I can get to them. Let's see. First question I see here is, what's the minimal dimensions that a strain gauge can have? So, the strain gauges, since we're placing strain gauges in nominal areas, we don't have to get, the absolute, microscopic size strain gauges that you sometimes like to use in high strain gradients. We're putting strain gauges in nominal areas. So just a nominal type of strain gauge that you use. So I'm sorry, I'm going to use inches here. Like a 50,000 size strain gauge, 60,000 size strain gauge is pretty typical. And the elements are, we're getting the strain matrix from the centroids of the elements. So the centroid of the element is basically averaging the strain data over the size of the element. So since we're going to be in low strain gradient areas, the strain gauges average what's the strain underneath the strain gauge. the element, averages the strain that was underneath the element. So that's kind of a way to think about this. So you could have strain gauges as large as the elements of your FEA model if you wanted to. All right. Let's see. Got a question here. Does TrueLoad work with ANSYS? So as of September of last year, we've introduced a version of TrueLoad that works with any FEA code. So ANSYS, NASTRAN, anything Abacus, anything that you want. Okay, so we can work with that. Let's see. Let's see, there's another question here about gauges. Do you need to use rosette gauges? So TrueLoad, the way it's designed, is to work with uniaxial gauges by default. We can work with rosette gauges, and basically by doing some clever FEA modeling and stacking of membranes or putting strain gauges very close to each other at 0, 90, and 45 degrees. But by default, the way that TrueLoad wants to work is just going to place uniaxial gauges at locations on the model. Okay. Let's see. We have another one here. What is the maximum operating temperature for a strain gauge? I am not a strain gauge technology expert, even though my program works with strain gauges. But typically, strain gauges, typical strain gauges can work probably up to, you know, probably a couple hundred degrees C. And then if you're getting to very, very high temperatures, you know, thousands of the, you know, 600, 700 or 1,000 degrees C, there are specialized high temperature strain gauges that that you can use. I've used them in my past, working on exhaust systems and cylinder heads of engines. I know they're out there. There's special care that you have to do, that you have to use in placing them, and they're expensive, but you can use them. Let's see. I think here's my final question. Does TrueLoad handle nonlinearity? So TrueLoad can handle nonlinearities, even though the basic mathematics is a linear F equals KX type of mathematics. There's several nonlinearities we can handle. We can handle contact nonlinearities if you have unit loads that represent the contact load, the load of the contact. So if you think of a cantilever beam that was maybe bumping up against the stopper, you could put in a unit load where that stopper was, and then if the beam doesn't contact that stopper, then that load's going to be 0. And when you do contact the stopper, the load will go to being non-zero. If you have other types of nonlinearities, like let's say, for instance, you're working with a part that has that does not obey F equals KX. So that would be a typical example of that would be like an engine mount in an automobile. So an engine mount is a hunk of rubber, and we can't really lay strain gauges to understand that. But what the beauty about these very nonlinear things is they typically are attached to the component via brackets that behave linearly. So we could take that engine mount and take the bracketry that holds onto the engine mount, and we could put strain gauges on the upstream and downstream side of those brackets and turn each bracket into a load transducer. And then we can get the loads going into and coming out of the engine mount by turning the brackets into load transducers. And then if you wanted to do FEA analysis to the engine mount, then you could take those time histories of loads and apply them to the nonlinear FEA model of that elastomer engine mount, and you could do a full hyperelastic analysis there with the time histories of loads that you measured. And you could even go as far as then take that hyperelastic nonlinear loading that you just measured with TrueLoad, and then you could take that whole time history of stress and strain results, and you could bring that off to a tool like FE-Safe Rubber to do the fatigue analysis on the rubber. So now you've got a very accurate field correlated loading history going into your rubber component in order to do FE-safe rubber analysis. So sometimes you need to think about the part and invert the problem a little bit. And if there's a nonlinear part you need to get the loads on, it's probably hooking up to some linear parts you can turn into the load transducers. Okay, Audrey, I think that's all the questions. Is there anything else you need to say here?
I think just had another question. Someone is asking, is it possible to get a copy of the recording? Definitely, yeah. We are recording this session at the moment, and every delegate of today's webinar will receive a copy for the link once we compile it. So you should get it in the next couple of days, an email with a link to the recording. So you should have access to the full recording. Okay. Okay. Right. Thank you ever so much, Tim. That was an excellent presentation and on time as well. So well done. I'd like to say as well, if you do have any more questions that you have after the webinar, please don't hesitate to email me or Tim, and we will be happy to answer this for you. I would like also to emphasize that if you do have any specific requirement, Tim and I would be happy to take this in one-to-one, and maybe we could do you a more specific demo related to your type of work. So please don't stop here. You know, we would like to hear from you, your feedback about what you saw today. Okay, this stage, I'd like to thank everybody and Tim for giving this excellent presentation, and thank you ever so much for joining us today, and we hope to hear from you in the future. Thanks very much.
Great. Thank you all. Great. Bye-bye.
Thank you. Bye-bye.